We start up again. Beginning now with the stability, starting with the easiest equations, advection. Actually, it's not easy at all, but it looks easy. So we create an advection equation that is linear. I want a time derivative, and then I need now a constant velocity. So here I invent some a0, and then the x derivative equals to 0. So it's a linearized version of the real thing. This is a hyperbolic equation. Hyperbolic with characteristics dx dt equals, and I'll write plus minus a0, but actually a0 is a parameter that I choose. So of course I can choose both positive and negative. Now we want to solve this one numerically. How to do that? You write down an FTCS scheme. This is where you start. FTCS, forward, time, central space. FTCS, thank you. Central space. So this is something I demand from you guys on an exam. Set up an FTCS scheme for this equation. Meaning forward in time, central in space. For this one, if we now discretize in the space, I use j. In time, I use superscript n. So a time derivative, first order, should then look something like this. N being the old time level where we know everything, n plus 1 is the unknown. First order in time, and then we have a0, and then I have an x derivative. So here I want a central space scheme. You have to create a derivative centralized around your focus point j. So of course you're going to need j plus 1. And you're going to need j minus 1, time level n, divided by 2 times delta x. This one now equal to 0, which is not true, of course. It's not equal to 0. It is equal to order delta t, delta x square. First order in time, second order in space. FTCS schemes are typically where you start. Very easy to implement, to create, and to program. It's pure explicit, so you know everything at time level n. Very easy to obtain time level n plus 1. So no problem so far. We can rewrite it a little bit. If we now write it on the form you are going to program this one, then you'll say I have my unknown to the left, that is uj n plus 1, and then you throw everything else on the other side. What do you get? Well, you will have 1 uj time level n, and then you will have something like a constant multiplied with the 2 other guys. So the constant I call a large C, multiply then with uj plus 1 minus uj minus 1. and my constant c equals, he will now be delta t multiplied with a0 divided by delta x, which is quite so famous. It is called a Courant number. He includes delta t, so here I can hope to find a criteria for him. Then that will also include a criteria for delta t. So how big can this Courant number be? How to find it? Well, we had this drawing actually before. You have time here, we have space, and here I have my center point J. So let now the x-axis be time level n. So you know everything at time level n. You know it at point J, you know it at point J plus 1, you know it at J minus 1, and so on. So you know everything here. But you see our scheme, he is only dependent, the new one is only dependent on these three from J and J plus minus 1. So this is the only region in space that we have sort of an initial condition for the next unknown time level up here. I want to find the solution n plus 1. What is it up here? Well, this is my discretization star, these 4 points, finding the new one based on these three down here. What was the philosophy then when you have a hyperbolic systems? The information is traveling along the characteristic lines. So my choice of delta t, the distance here, you can sort of see it geometrically. If your characteristics does not go below this point, if the characteristic curves, if they go something like this or like this, then it's okay. Here you will have the slope will be minus a0. Here the slope will be plus a0. Information from this point traveling with a positive velocity a0, and from this one with a negative a0. So they meet at this point. And the triangle, the green triangle there, was the solution area, the only area where you could find an entire solution. Because if you go outside, then say you wanted a solution all the way up here. That's not possible. You're missing information. You don't have the information from this point. It doesn't enter into my discretization scheme. If I had chosen a higher order method, saying this one should be expressed with, say, delta x to the power of 4, then I might have to use j plus 2, j minus 2. Then I could have increased the time step, yes. Or if you choose a more advanced time step than just a forward Euler scheme, yes, it would be possible. But here, the very simple scheme, say, you can't choose a time step bigger than this point. Or to put it in another way, if you look at the Courant number, here you have one single computational cell. So here we have a delta x. Here you have a velocity entering into your mesh, your cell. Call it a0. Now during one single delta t, we are concerned with what's happening with this cell. We are just focusing on this cell. What enters, what exits. We don't see what's coming from far above or far the other way. We are only concerned with sort of the closest neighbors. So that means during one single time step, the information traveling with this velocity must not be longer than 1 delta x. So the criteria should read something like this. A0 multiplied with a time, that's a distance, must be smaller or equal delta x. That should be sort of a physical demand here. Only taking the closest neighbor into account, then this has to be the case. Meaning, of course, that the Courant number must be smaller or equal than 1. This is what is called a Courant Friedrich-Levy condition. A CFL condition for short. Nowadays people tend to call it just the Courant condition, but all three guys were actually authors of this expression, so they should all be credited. And here actually this A0 could be both positive and negative, so actually you should write it like this, absolute value. Any questions to that one? Should be sort of intuitive. We have not used any stability methods, and actually the stability analysis here is dead wrong, but that's another story. But I mean, it's quite possible, should be quite possible to sort of accept the logic behind it. You should not go further than one cell length during one single time step, because my discretization scheme doesn't cover that. I don't have j plus 2 or j minus 2 here. So you have to keep yourself limited to one single time step. And then to be just looking at the closest neighbors. This demand can be a little bit tricky, because you really don't know it in advance. Say you have a problem, something like this. You're sending in a velocity into a domain, then you have a wall, and then you have sort of a small narrow section here. Of course, the velocities here, they are going to be very big due to continuity. And typically what you have to do when you are meshing up this domain here, creating a grid system, something like this, doesn't have to be rectangular of course, but typically here you are going to need a lot of cells, because here you have a lot of actions going on, a lot of motion that you have to resolve. So here you have to use very small delta x, small delta y. And there you have a big velocity. Thank you very much. Then you see the problem. You're going to have a very, very, very small delta t because of this region. High velocity and small delta x. That's not good, but unavoidable. You can't really help it. Well, one remedy would then be using higher order methods, of course. But that can be a little bit messy, especially when you are getting close to a boundary. I mean, as a boundary condition, we used ghost cells. So if he is inside the boundary, then okay, we have to find a value for him. If you have 2 points or 3 points or more points inside the wall, thank you very much. That's not fun either. So it's quite tricky with higher order methods when it comes to the boundary conditions. Okay, that was sort of the first step, a Courant-Friedrich-Levy condition, which is actually the first criteria stated in the Navier-Stokes, the Sola algorithm. There we have a reference velocity of 1, so I just say delta t actually has to be smaller than delta x, if this one is allowed to be 1. But then I don't take things like this into account. So actually what you should do in computer code, you have to investigate this criteria for every cell, the delta x might change, and the local velocity. So this should be investigated for every cell in every time step. That can be a little bit boring, of course, but actually that's what you should do. You can't really guess this in advance if you have problems such as this one. So they should be continuously controlled and checked locally. Well, actually, what it says in Sola, if I recall correctly, it says delta t has to be smaller or equal delta x over u, delta y over v. And then the smallest one of these two. But I think I only used the velocity, the reference velocity, and then you see it's only delta x. But that's what it should have read if it had been more accurate. Okay. Any questions to this one? Yep.
How do you determine A0 when you...
Are you thinking here when you do the linearization?
Yeah.
Well, that's sort of your choice. When you have the real thing, this term here actually looks something like this: u du dx, and then v du dy, and so on. So actually, this one is not constant. It should be the u directly, but you can't do it if you want to do a correct analysis. So if you tried it, well, here with this way to look at it, then these characteristic lines here, they are not straight lines anymore in general. They can be curved lines. So you don't know. I mean, they will be a part of the solution actually. So they can change as this one now becomes the real thing, the real u.
So if the velocity change is not steady and changes with time, then the closed number will.
It also will change, yes.
So I cannot really predict.
No.
How it is.
You can't. And also you can see it can change from place to place. So this is a situation here, but for the next ones, this one, he might go something totally different, and this one even totally different. You have no idea. When this is sort of a general unknown, you can't really tell. So the best you can hope for, linearize. Of course, you can cheat a little bit here. This is one way to do it. Instead of A0 here, I use the local velocity uj, but then I take the very old one, n minus 1, from the previous time step. That could be one way to linearize this one. And then you see the error is not so big. So, I mean, you have tricks like this to work your way around it. So call this one, say, a semi-linearized or something like that. That could be one way around it. But to have it straightforward, you need a constant there. Other questions? We'll come back to this equation because this is not the entire truth. The next step was the diffusion equation. The first and the last term in the Navier-Stokes. So a one-dimensional diffusion equation. You should look something like this. Time derivative equals viscosity, double derivative with respect to x. One-dimensional diffusion equation. This is parabolic. So it has only one characteristics. And that one reads dx dt tends towards infinity. So the information sort of spread out in space instantly. And this equation will describe things like startup of a Couette flow, startup of a Poisson flow. We have seen this one already. And Stokes' first and second problems, quite famous. Here, an infinite plate. Fluid above is at rest. When t equals 0, all of a sudden this wall starts to move with a constant velocity. And you will start then getting velocity profiles looking something like this as time goes by. So they will sort of develop like that. That's Stokes' first problem. Stokes' second problem. Similar, you have a wall. Everything is at rest, and then time equals 0. You start oscillating this wall with a v sine omega t, something like that, harmonic oscillations, and you will get velocity profiles. They will look something like this. Can be quite strange. Classical problems, Stokes' first and second, possible to solve analytically. So this equation describes these phenomena. Here I want to write it in with dimensions. I used the kinematic viscosity already, so now I write wave on top of all my variables just to tell these quantities now have dimension. And then write it in a dimensionless form. We need a length, L. Of course, for these problems, you have trouble finding a length scale. You have one wall which is infinitely long, so that can be a little bit of a trick. It's not our problem, so never mind. Velocity scale. So there I just used a big U. And then the time scale. And then we choose the viscous time scale. Length squared by kinematic viscosity. Kinematic viscosity had dimension meter square per second. So yes, we will have something with time when you do it like this. And this is a time scale, the viscous time scale, for information traveling in the cross stream direction. So from the wall, the viscous effect will sort of spread out here upwards and here also upwards. So this one should be the proper time scale, which you then will see when you insert these scaling into your equation. I mean, you have now a non-dimensional velocity. It's one with dimension divided by big U. X without dimension, you just divide by L. And time, you take the one you have in seconds, and then you divide by this strange time scale, multiply with viscosity divided by L square. There you have the non-dimensional parameters. Insert these into your equation, and what do you get? U wave will now be large U du, and then we have dt. Inserting a t wave, we will have L square down here. Viscosity comes up, and then the time derivative. And what do we have on the other side? We have viscosity already. For the velocity, that's 1u outside, du, and on the bottom you have 2 x's. So that will be L square. Dx square. And then you see all the scales disappears, everything. So the non-dimensional version is very simple. Du dt equals double derivative du square dx square, like that. So yes, the time scale was a good choice. No parameters entering into these equations. Now for the stability. Find an FTCS scheme for this one. FTCS. Okay, we use the same notation as last time. You will have center point, time level nu, minus the old one, divided by delta t, equal, and then on the other side, now double derivative, which reads j plus 1 minus 2 times center point plus j minus 1 divided by delta x square. There we have it. And then we rewrite unknown n plus 1 equals and throw everything else on the other side. Here we are going to have a quantity, not the Courant number. Now I have delta t by delta x square. So that one we baptize small r. Delta t by delta x square. So how can we rewrite the equation now? The new one equals the old one, ujn. He will have the 1 from him, then minus 2r from this one. While these two, j plus minus 1, will be multiplied with just the r. uj plus 1 plus uj minus 1. And so there we have our recipe for our program. Pure explicit, no problem there. Question is the choice of delta t, meaning the choice of the value for the r to keep it stable. That is the question. Any questions to this one? It's okay. Just as an example for use of the von Neumann stability criteria, you have been given here a stability analysis with von Neumann. Sadly, this one is in Norwegian, but you should be able to follow it quite straightforward. And I've chosen this one because he uses the exact same equation as an example. So the philosophy here, if you have a linear discrete equation system, then you can actually find, define an error between your the analytic solution and the exact solution. And then if you insert it, you'll find that your operator here, your equation system, he will of course be fulfilled if you have the exact solution, but inserting here you can rewrite it and find that the error itself actually also fulfills your equation system, as long as it is linear. So, as an example, we look at the diffusion equation, and here just to find some solutions, sort of a cheating here for this example. So we know the solutions, we can insert them and see that yes, they are indeed a solution of this equation. Now we sort of look at what's called an amplification factor. Look at the difference between the new value versus the old one. If this amplification factor is then bigger than 1, then you're in trouble. Because if you know this amplification factor, you can write the solution at time level n plus 1 equals the amplification factor times the previous one, and then from the previous, then we have g squared, and then all the way down to the first one. Meaning your final unknown here is based on your initial value multiplied with this amplification factor to the power of the number of time steps, which can be a very big number. So of course, if he is bigger than 1, he's going to explode. It's going to be unstable. That's the philosophy behind the von Neumann method. And then we say the adder itself can be sort of expressed as one arbitrary term in an Fourier series. So here, this beta here will be an arbitrary wave number. Just one arbitrary adder wave, you might say. And then we use him to calculate what will the amplification factor be. As long as this one is an arbitrary term from the Fourier series, he should cover everything. And indeed, when you insert it, you have a linear equation system, the wave number is going to disappear. It doesn't really matter what it is. So yes, this actually should be quite precise. So the criteria, then amplification factor must be smaller or equal to 1. But it has to be linear, and also one thing, sort of here between the lines, it's a Fourier series, or based on a Fourier series, meaning your domain has to be periodic. So whatever you send in goes out on the other side. You don't get your boundary conditions into the equation system at all. So he does not cover the boundary conditions. Typically, you can have different criteria from the internal domain versus criteria arising from the boundary conditions. So the von Neumann can be dangerous. It doesn't cover the boundary conditions. So how to use it? You have the example here. You set up your discrete equation system, but with the adder. E here now being the adder. And for the adder, you insert the amplification factor and then multiplied with this term here, which then should represent a given arbitrary term in a Fourier series. So here you will have gn plus 1 to the left and multiplied with this. On the other side, from all terms, you will have g to the power of n, which then when you divide by gn, you will have just g left. Also, this term, well, here you have to pay attention. You have y in the center point, the distance. Here you will have y plus 1, here you have y minus 1. So you will have a little bit of algebra typically when you are dealing with this method with e to the power of plus minus and so on and so forth. And in the end, you need some algebra here to find the stability criteria. your G has to be smaller than 1, implies this R, that was delta T by delta X squared, has to be smaller than this expression here in general, and it will be fulfilled for any deltas here, as long as no, that should be quite okay. Yes, so we should have this R between 0 and 1/2. So that is the demand that we get from the von Neumann stability analysis. So I'm not going to require that you know this method, but you should definitely be familiar with it. Okay, R must be between 0 and 1/2. Von Neumann. Implied 0, bigger or equal R, bigger or equal 1/2. Bigger than 0, of course, not a problem. You have positive, positive, so no problems there. So it's this part that is interesting for us. And keeping him smaller than 1/2. What will that mean? So delta T by delta X squared smaller or equal 1/2. And then, well, write it like this. Delta T smaller or equal 1/2 delta X squared. Now, this is written in a non-dimensional form. Insert the scales. Insert with dimensions, or just scales, that's okay. What do you get? Delta T. So delta T in seconds. We then have to multiply with viscosity, and we have length square, smaller or equal 1/2. And then insert for delta X. Delta X wave square must then be also an L square there. So the length falls, and you are left with the criteria delta T with dimensions must be smaller or equal than delta X square by 2 times the viscosity. That's the demand with dimensions. And this one actually you can find in the Sola algorithm as well. Although there it's written, I think, a little bit more complex. No, it's actually written more easier. Yes. No, it's a little bit more tricky than that. So in Sola you will have something like delta T. Remember that one is also non-dimensionalized, not with the time scale that we chose there, but the time scale L over U. So there the demand will be something like this. You will have 1 over viscosity, that's actually the Reynolds number, and then delta X square half. So he will read something like that, but that's just for a one-dimensional problem. So in a two-dimensional problem, he will read that one a little bit differently. It will actually be 1/4 here. But never mind, you'll get the idea where he comes from. Any questions to this one? Okay.
This one called R can't be 0, right?
Sorry?
R can't be 0.
R cannot be 0. That would make no sense at all.
So the range of R is like bigger than 0.
Yeah.
smaller than
Yeah,
okay.
but he can be very close to 0 if you want. You can have very, very small delta t's if you like, of course. Yeah, just to show you, if you choose, you don't have to write this down, just to show you, use a matrix method. For the same problem. How to do that? Well, you will write the algebraic equation system in a matrix form. How will this matrix looks like? Well, you'll have one huge coefficient matrix multiplied with, and here comes now all your unknowns. U1, U2, U3, all the way down to UN or whatever. Equals, and then you'll have the right-hand side. That should then be any constants, any whatever, and that should then read, okay, we write this, UN equals, no, now I'm mistaken. These are time level n. Here are your unknowns, 1, 2, 3, all the way down to UN. Time level n plus 1. Because we have it explicitly. So this will be your unknowns. These are from the previous time step, so they are known, multiplied with a coefficient matrix. How will he look like? Well, you will have the center point having this coefficient 1 minus 2r. Of course, that one you will find all the way on the diagonal, all the way down here, 1 minus 2r, so that's okay. But then you need the neighbors. So here you will have one band of r, all the way down here, and also down here, and r all the way down here. That will be roughly your equation system, and then the rest is zeros. So for a 1D case, it will be a very nice 3-diagonal matrix. But now you see you also can take the boundary conditions into account. Here we haven't said anything about the boundary. But here, of course, if this is your first unknown, number 1, he should then be multiplied with this one. Number 2 has an r, that is this one. But what about this guy, j minus 1? That should now read something like u0. Well, he's outside the matrix. So that means u0 has to be included by something strange here. So here, for the first one, you might get something else. just because of the boundary condition. And also the last one, that's the other boundary. You might have to reformulate this one to cover for the boundary conditions. So say these guys must cover the boundary conditions. And then you start doing the analysis. Then you look at this coefficient matrix, this big coefficient matrix A, and then you have to find the eigenvalues, the eigenvectors for these for this one, and say for the entire equation here, the matrix, the eigenvalues for this matrix has to be smaller or equal to 1. So there's sort of a spectral radius smaller than 1. You have several numerical theorems covering the numerics there. We are not going into that detail. It can be hard to find them in a general case. 2D, 3D matrices can be quite complex. So you might say the matrix method, he covers more than the von Neumann. For Neumann, he assumes periodic boundary conditions, cyclic boundary conditions. The real boundary conditions does not come into the analysis. Matrix methods, much better. Okay? What we are going to do is the nasty, dirty, quick, simple method, max-mean method, or the method of positive coefficients. Very simple and very easy to use, and the philosophy behind it also very easy. So we can use this one as an example. Say max-mean method. We have an unknown x, and he can be represented as a series A1, x1, A2, x2, yada yada yada, all the way up to some AK, xk. Then we define the smallest x, x mean. That's the smallest of all of these x's, x1, x2, all the way up to xk. And we also define the maximum. That is the biggest one of all of them. So then we sort of have these two as limits. That would be very interesting, because now we can write the following. Then we can write up the following. If I take the recipe that we had up here and substitute in for all the x's, you choose the smallest one and put him outside. Then you can write something like this: the smallest x multiplied with the sum of the coefficients only. That must definitely be the lowest possible value that my new x can have. So my x is going to be bigger than this, definitely. And then also he's going to be smaller than, if you do it the other way, take the big x outside and then the sum of all these coefficients. That sort of has to be the case. Now we have a couple of ifs. You can do this if all these coefficients here, say, let all A coefficients be positive. And also let the sum of all these coefficients be equal to 1. If that is the case, then you have it very nicely. Then you can write directly x mean smaller or equal x smaller or equal x max, implying stable, because your x is bounded. He has to be in between those two values, meaning he will never explode, no matter what. But you have two ifs. All A positive, and the sum of the coefficient must be 1. Let's try that method. And we have the example ready. So we check the sum of all coefficients. Well, for my first one, uj, I have the coefficient 1 minus 2r. For the next one, j plus 1, I have the coefficient r. And from the last one, well, I also have the coefficient r. And the sum is 1. Okay, I can use the method. And this happens quite frequently with these simple FTCS schemes. Sum of all the coefficients is going to be 1. Very nice. Then you demand all coefficients. Write an upside down A, meaning for all coefficients must be bigger or equal to 0. Well, the r itself, yes, is going to be bigger than 0, of course. So these coefficients, these two, they are not a problem. The first one is the problem. So there you see 1 has to be bigger or equal than 2r, meaning r has to be bigger or equal 1/2. So there you see you get the exact sufficient criteria with this very simple method. And it is actually so simple you could use it in your head. From this one you say 1 minus 2r plus r is 1. Okay, all coefficients positive is only this one. R has to be smaller than 1/2. Very simple method. But frequently it's exactly what you need. So why make life difficult? Yeah.
R is smaller than.
Sorry, yes, of course. Not bigger. Thank you. R must be smaller than 1/2. Other questions? We take a break.